Thank you for joining this lesson. We're going to discuss radioactivity. This is our Form 4 physics topic. We are told that the diagram below shows one of the detectors of radiation. Therefore, this detector of radiations is having a thin mica window. We are also having a part B here and also another part A. Then we are having a ratimeter here. Then we have a high potential here, 450 voltage, whereby there is a positive, there is a negative, and there is also a positive terminal here. Then we have a resistance. Identify the device. This is a GM tube. In full, we call it the Ginger Muller tube. Yeah, this is the GM tube for detecting radioactive substances. Now we are told again to name the parts labeled A and B. So part A is the aluminium casing, which is the cathode. So it's the cathode. Aluminium case. It's an aluminium casing which acts as the cathode. And we are also having the anode now, which is part B. So this metal B is the anode in this case. After that, we are told to explain how radiation entering the mica window is detected. First of all, we usually say that the mica window is made thin. Even according to the description here, it's called thin mica window. Therefore, the radioactive enters the thin mica window. The radiation enters the thin, or enters through the thin mica window. It's made thin to ensure that all the radiations, can enter, ionizing the gas particles in the tube. So now once the radiation enters, we know that radioactive substances have what we call ionization effect. So they ionize the gas in the tube, and now the positive ions are attracted. The positive ions are attracted by the cathode. The positive by the cathode, while the negative ions are attracted by the anode. And after that attraction, now we say that a potential difference is created. So we can just continue explaining. A potential difference is created, leading to a pulse current. So there is a pulse current which now is taken to the ratimeter, and the ratimeter now will rate the amount of pulses, and the amount of pulses, or the rate of creation of the pulses, will enable us to know the intensity of the ionization which has been caused, and with the amount, or with the intensity of ionization, we will be able to estimate the radiation which has entered through the mica window, because you know that all the radiations don't cause the same effect when we come to ionization. We have alpha particles with the greatest ionization. That means the pulses are going to be faster the rate of creation of pulse currents is going to be faster in the retimeter if it is an alpha particle which has entered, followed by beta particles. Then finally we have the gamma radiations, which have very little or even no ionization effect. So now we are told again to a question here: a small amount of halogen vapor is usually present in the tube. What is the purpose? The purpose of the halogen vapor, it acts as what we call a quenching agent. A quenching agent. This means the halogen vapor is going to absorb the energy which is in the positive ions. Otherwise, they will cause further ionization, and that might lead to a false pulse being registered. A secondary ionization might occur if the energy in the positive ions is not absorbed. Therefore, the halogen vapor acts as a quenching agent, and to quench the system there is simply to absorb. And after absorbing the energy which is in the positive ions, now we reduce the chances of causing secondary ionization, which might register a false pulse in the retimeter. So that is the purpose of the halogen. We can look at a part B here, which is from photoemission. It's a different topic. Photoemission, we'll answer this one, then the other part of the same will be answered in a different video. The setup below shows UV light striking a zinc plate placed on uncharged electroscope. So this electroscope is uncharged, and now we have UV radiations now, which are incident to a zinc plate. What we should know is that because this is a metal plate, first of all, we are told to state and explain the observation made. So we are assuming that the UV radiation which is approaching the zinc plate is having enough energy to cause photoemission. So photoemission occurs in this place, and electrons are produced. Those electrons will attract the positive ions, but repel the negative. And because the negatives will split themselves onto this metal rod and to the leaf, so we will have both on the plate and on the leaf, the negatives which will be repelled will get spread, and that is why the leaf divergence is expected to increase due to both charges here. Negatives will come here and also on the leaf. So you will say observation is that the leaf divergence increases. The leaf divergence increases. The leaf divergence increases. That is our observation. How can we account for this observation? We are saying the UV radiation or UV rays cause photoemission, or rather photoelectric emission on the zinc plate. On the zinc plate, making this will make the positive charges on the cap of the electroscope, making the positive charges on the cap of the electroscope to be attracted while the electrons are repelled. Now, after repelling the electrons, now I'm saying they will distribute themselves onto the plate and also onto the leaf. That will make the leaf to diverge more from the plate, because we will have positive electrons and also positive electrons on the leaf. And now that they are similar charges, then we expect a repulsion. So a repulsion between the plate and the leaf is what will cause an increase in the leaf divergence. Remember, you can keep consulting us through 0704 153 366. Ask questions, and you can also join our online classes through the same number. Thank you. Subscribe and share.